Okay, so for the next part of the video, I'm going to cover special cases, several special cases in a distillation column, and what kind of modifications that we should do in the material balance equation whenever we have these special cases. So let's have a look at the first special case, the stripping column distillation. Okay, so what is a stripping column distillation? So in some cases, the feed to be distilled is not supplied to an intermediate point in a column, but rather it is added to the top of the stripping column. So meaning, simply say that instead of having a two part of a column, like normally you will have a feed in the middle, and then you have the condenser, and then you have the DL, right? This is the normal column. I mean typical column, not to say that this is not normal, but so whatever above the feed section is called rectification, and whatever is below the feed section is called the stripping section. So in this case, we don't have the rectification section, we only have a stripping section for the column. So yeah, that's why it says that in this case, the feed is fed from the top of the column, okay? It's not from the middle of the column, so rather it's fed from the top of the column. So normally in this case, the feed is usually a liquid, a saturated liquid at its boiling point, and the overhead product VD is the vapor rising from the top plate, goes to a condenser or whatever happens here, but there's no reflux return to the tower. Okay, so there's no reflux. So that's why it is called a stripping column distillation, because it only does, all it does is stripping. Okay, so maybe there's a condenser here. Okay, maybe there's a condenser and convert all this VD into liquid. Okay, D and XD, but we don't really care whatever happens there for now. Okay, so okay, that is what happens at the top of the column, and the bottom's product B here contains a high concentration of the less volatile component. Okay, so in this case, the whole column operates as a stripping tower, with the vapor removing the more volatile component from the liquid as it flows downward. It strips the more volatile component from the liquid flow rate. Okay, so there is no rectifying section, no enrichment section in the column. Okay, so how does this make it different in our material balance? Okay, so okay, just have a look at the column again and assume a constant molar flow rate and constant molar overflow as well. Component material balance on the more volatile component around the dashed line will give you this. Okay, around the dashed line. So first you can do overall material balance first. LM input equals to output Vm plus 1 plus B. Then when you rearrange, you have Vm plus 1 equals to Lm minus B. Then when you put in the component composition, Ym plus 1 equals to Lm Xm minus B Xb. Then you put Ym plus 1 as the subject of the equation, you will get this equation here. Okay. Then the stripping operating line equation is the same with the SOL of a complete tower. It looks the same. Okay, this is the SOL because it's only a stripping column. Okay, it intersects with the y equals to x line at x equal to xb, and the slope is still Lm over Vm plus 1. And if the feed is a saturated liquid feed and assuming constant molar overflow CMO, then the Lm here equals to F. Okay, liquid flow rate same with liquid flow rate, vapor flow rate same with vapor flow rate. Okay, but if the feed is a cold liquid below the boiling point, then the Q line should be used, and when Q is greater than 1, you will have Lm more. I mean, greater than the liquid feed because some of the vapor will be vaporized. Okay. Let's straight away do an example on a stripping column distillation. So read the question. A 400 kilomole per hour liquid feed at the boiling point containing 70 mole percent benzene and 30 mole percent toluene is fed to a stripping tower at 101.3 kilopascal pressure. The bottom's product flow is 60 kilomole per hour containing only 10 mole percent benzene and the rest toluene. Calculate A, the kilomole per hour of vapor and overhead vapor and its composition, and B, the number of theoretical steps required. So this is the given equilibrium data. And then we can try to solve for part A first because it's material balance. So you draw the diagram. So this is your stripping column where you have the feed and XF. So the feed here is 400 kilomole per hour. Feed composition is 0.7. And then your B and XB. So XB is 0.1 and B is 60 mole. So you can do overall balance. F equals to B plus VD. So because F is 400 and B is 60, so VD is 340 kilomole per hour. And then you can do a component balance. Fxf equals to VDYD plus BXB, and you put in all the numbers except for YD because this one is still unknown. So then you can solve for YD. So YD equals to 0.806. So that is the composition at the top. Okay, the vapor composition. That is the kilomole per hour of overhead vapor and its composition. For part B, we need to calculate the number of stages. So similarly, first thing first, we need to draw the VLE. Then we draw the Y equals to X line. And then our XF, the feed condition, Q equals to 1, right? Because it's a liquid at its boiling point. So you can just draw a vertical straight line through 0.7. Okay, starting from here, you just draw this vertical straight line that you can see, the green line. But then where do you stop to get the YD? So YD, just now we calculated YD to be 0.806. So looking back at the equation just now, so this is a material balance equation. And you know that operating line is actually same with material balance equation. Okay, so here the coordinate of XF will give you the coordinate of YD. Here YD is 0.8, okay, Y and X. That is your coordinate. So that's why we draw a line at Y equals to 0.806 here. So this is our starting point where we need to step off the stages. Okay, so you step off the stages 1, 2, 3, 4, almost 5, but we stop here because we only have to step off the stage until XB equals to 0.1. This stage number 1, 2, 3, 4, 5, but not reaching 5. So around 4 point, maybe 4.1, 4.2 stages. Okay, do we have a reboiler? Do we have a reboiler for stripping column? Yes, we have a reboiler. So this stage includes reboiler. So this final stage here is the reboiler stage. Okay, so that's how we calculate the number of stages for stripping column. Next special case is the rectifying column distillation. Okay, so unlike the stripping column distillation, so in rectifying column distillation, there is no stripping part. It's only rectification part. As you can see, compare it again with the typical distillation column. You have feed. So this is your rectification section, condenser, reflux, product. And then you have reboiler, bottoms product, vapor. Okay, but here you don't have. You just stop. You don't have at all the stripping column. So what you have is a rectification column, like what you see in the diagram here. Okay, so rectifying or enriching tower is where the feed enters the bottom of the tower as vapor. Okay, and then the overhead distillate is produced in the same manner as in a complete fractionating tower and is usually quite rich in the more volatile component. Okay, so if the feed is a saturated vapor, so assuming constant molar overflow, CMO, then feed is vapor, so F equals to V. Okay, F equals to V. If the rectifying operating line is also the same as before. The ROL still the same. And the Q line equation holds too, because it still holds. So it's the only difference is that there is no stripping section in the column. Okay. So again, assuming a constant molar overflow, this is L. So L equals to B. The liquid flow rate equals to liquid flow rate, vapor equals to vapor. But the composition changes from plate to plate. So let's do an example on rectifying column distillation. Okay, so a rectifying tower is fed 100 kilomole per hour of a saturated vapor feed containing a 40% mole benzene and 60 mole percent toluene at 1 atm. The distillate is to contain 90 mole percent benzene, so XD equals to 0.9. The reflux ratio is set at 4 to 1. Okay, so R equals to 4 lah. Okay, calculate A, the kilomole per hour of distillate and bottoms product and their compositions. And again, the number of theoretical plates required. So let's do part A first, the material balance. So you draw your diagram. So given F is 100 kilomole per hour and XF is 0.4. XD you want it to be 0.9 and the reflux ratio set is 4. So do a material balance on the top of the column. V equals to L plus D. So because R is L over D equals to 4. So you know that you can just rearrange to get L equals to 4 times D. Feed is a saturated vapor. So V equals to F. Okay, it's constant molar overflow. So you can just keep put in the value of V equals to 100. And L is 4 times D, so just put in 4D plus D. Then you can solve for the D. So you get the D equals to 20 kilomole per hour. And then you can solve for B. Okay, so overall, just rearrange here and you get the B equals to 80 kilomole per hour. And then you can do a component balance. FZF equals to BXB plus DXD, like the normal distillation column. And you know XD, you know XF or ZF. Now you don't know XB, so the unknown is XB equals to 0.275. So that is part A. Then part B is to calculate the theoretical number of stages. So in this case, first of all, again, you draw the VLE. You just draw the Y equals to X line. And then this is your starting point of your ROL. So your ROL, okay, let's do ROL. So ROL is yn plus 1 equals to R over R plus 1, xn plus xd over R plus 1. So in this case, is yn plus 1 equals to 4 over 4 plus 5 is 4 over 5 is 0.8 xn plus xd is 0.9 over 5. So 0.9 divided by 5 is 0.18. So that's why here is your 0.0 and 0.18. And here is your xd 0.9 and 0.9. Okay, so this is your Q line because Q is a saturated vapor, so Q equals to 0. So it's just a horizontal straight line starting from XF equals to 0.4. So that is your Q line. Yeah, so then we step off from XD. So 1, 2, 3, 4. So let's have a look whether or not this is our same with our XB, because our XB just now when we calculated, what do we get? We get 0.275. So XB is 0.275. So by right, we should stop somewhere here, right? So this is 0.25, 0.26, 27, 28, 29. So about here lah. Okay, so 1, 2, 3. This is 4, but we don't go all the way there. So maybe it's about 3.7 stages. Okay, 3.7 stages. Is there a boiler? Is there a reboiler or not in this rectifying column? Look at the diagram again. No reboiler. So 3.7 stages is the number of theoretical stages required. Okay. Okay, I'm going to stop here first before we continue with the special case number 3.